All right, so here we go with part 2 of section 18.1. We're still working with probability density functions. And in this last bit, we're going to take a look at the idea of the cumulative distribution function. Okay? Now, the cumulative distribution function says, or reads, or is defined as, if you have some function f that is a probability density function of a random variable on an interval a to b, then the cumulative distribution function is defined as big F of x. Remember, little f was our probability density function. So big F is the probability that our random variable is less than some value x is equal to the integral from the lower limit where our function is defined to a variable x of f of t dt. Okay. Now, I know that looks kind of confusing, but here's what's happening. What's happening here is we have some function, some probability density function. Okay, and I'm just going to assume that here it is. That's my function. That's my probability density function, y equals f of x. It is valid on some interval starting at a value a and stopping at a value b. Right. Now, what if, for whatever reason, you were always doing this? You were always finding this area right here, this probability, where the lower limit was always a, but the upper limit changed. Well, the mathematics would say to find that probability, do the integral, but always start at a, and make the upper limit changeable, right, of your probability density function, f of t dt. Now you might be wondering why. Why did he suddenly make this a t dt when all the other examples you've done, that's been x dx? Well, it's because I'm a mathematician. And a mathematician would say that if you have a variable here, that variable can't be the same variable, because then you have a variable of integration that is the same as the variable that is your limit, and blah, 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 blah. Basically, those things can't match, because if they do match, I don't know, the world will stop spinning or something. I don't know, but I know that I'm not allowed to do that because I'm a mathematician, and I learned that. All right? So this is this makes a new function, though, because when I do this math, I don't get a number coming out of this. When I do this math, I get a function coming out of this, a function of the variable x. And what that function does is it always finds the probability that the random variable is less than whatever variable value you put in. And that's going to be our variable upper limit. It allows us to change our upper limit. All right, so this is what I want to do. This is a cumulative distribution function. Now, we've already seen these. We've already done these. Remember binomial CDF? When we found that left tail? CDF, the cumulative distribution function. You know that command we were using back in chapter 9, that normal CDF? Cumulative distribution function. Right? We're just going to make them for some given probability density function and turn it into a cumulative distribution function. So here, I want to find the cumulative distribution function for the two previous examples that I worked with. All right. So here's my function. Here's my interval. I want to find this, my cumulative distribution function. I know it's going to be the integral from a to x of f of t dt. And for this example, my a is going to be 4, and my little f is going to be that 1/11 times 1 plus 3 over the square root of t. And why did I change it to t? It's that x thing we were talking about a little while ago. Right? Now, unfortunately, as much as I hate to say this, these I have to do by hand. Right? So I'm going to set this up, my cumulative distribution function is going to be the integral from 4 to x of 1/11 times 1 plus 3 over root t dt. Okay? I'm going to clean this thing up a little bit. I'm going to treat this as a coefficient and pull it out in front. Right? And that's going to give me then that my cumulative distribution function is going to be 1/11 times the integral from 4 to x of 1 plus 3t to the negative 1/2 dt. Now I change that exponent just like I did last time when I did this problem by hand. Okay? I'm going to drag it up here over the top. I'm going to get then that my f of x, my cumulative distribution function, is going to be 1/11 times, and now I'm going to integrate. The integral of 1 is t. The integral of 3t to the negative 1/2 is going to be 3 times t to the 1/2 times 2 over 1 out in front, or just plain old 2. And this needs to be evaluated from 4 to x. All right, a little bit more work to do and I'll be done. F of x 1/11 times, let's see, plug an x in there. I'm going to get x plus 6 root x minus, plug a 4 in there, 4 minus 6 root 4, 1/11 x plus 6 root x minus, what is that going to give you? That's a 2. 6 times 2 is 12. 12 minus 16. So my f of x, my cumulative distribution function, is 1/11 x plus 6 root x minus 16. Okay, if you're wondering what's going on here with this wiggly woggly business, I don't know. My pen broke, I had to get a new one, and I think this one doesn't work quite right. So I might have to return it and get another new one, which is a pain, by the way. Okay, stupid pens are like $100. Don't break them. But there's my distribution function, right? I'm asked to do the same thing here for this guy. Find that cumulative distribution function. Here's my function, here's my interval, my cumulative distribution function. F of x is going to be the integral from 0 to x of f of t dt. Right? Plugging everything in, my f of x is equal to the integral from 0 to x of 1/2 e to the negative t over 2 dt. That 1/2 is a coefficient, so I'll pull that out in front. So that's going to give me 1/2 times the integral from 0 to x of e to the negative t over 2 dt. That's my f of x. Right. I'll integrate. That's going to give me 1/2 times the integral of e to the negative t over 2 is going to be negative 2 times e to the negative t over 2. Right? Evaluated from 0 to x. Right? Dragging that up here, I got my f of x, my cumulative distribution function. Let's see, plug in an x and plug in a 0. Okay, so that's going to give me, wait. Can I pull this negative 2 out and multiply it here and just make that be a negative 1? Times, and now I don't have to worry about that in there, I just got to worry about this guy. E to the negative x over 2 minus e to the 0. E to the 0 is 1, so then this is negative 1 times e to the negative x over 2 minus 1, or 1 minus e to the negative x over 2. And there's my cumulative distribution function. Now, if you're wondering what anyone would ever do with this, or with this, this is what they do. They would calculate probabilities where the lower limit is fixed and the upper limit changes. So for our first example right here, this was, what was that for? That came from this problem, right? Where I had a machine that had a useful life from 4 to 19 years. So then if I take this function and if I find f of 6, that's going to be the probability that the machine will last between 4 and 6 years. Or if I found f of 8, that would be the probability that the machine lasts between 4 and 8 years. Down here, this was the computer part problem. So if I found f of 9, that would be the probability that this part lasted 0 to 9 months. Or if I found f of 14, that would be the probability that this part lasted between 0 and 14 months. The cumulative distribution function always starts at the bottom for whatever your probability model is and stops at whatever number you tell it to stop at. It finds those left tails. And if you're like still not convinced, we did this I don't know how many times when we did these guys right here. The binomial CDF and the normal CDF. We found left tail problems all the time. Right? That brings us to the end of section 18.1. So I'm going to call it here. Have a wonderful day. I'll see you all back here for 18.2.